No, it's good now. We can hear you now.
Okay. I can't see anybody. So if the audience gets bored, somebody should do something noisy and let me know. I'm not a philosopher. I think that will become aware to everyone here who's not already aware of it. And my aim here is not philosophical. My aim is physical. Whenever they have these discussions of whether we physicists like philosophers and philosophers get in our way, and believe, you may not believe me, but we had such a discussion just last week at Perimeter, with the majority of the physicists saying, still what good are the philosophers? My position is they're very good. They're very useful, but that's not for any a priori reason of being well educated. It's because we learn things from you philosophers that we wouldn't otherwise know. And so my talk is in that lessons in that framework. Now let's see, does the screen should we change? Can you, somebody help me here? I have this big meeting chat in front of me. That was not the right thing to do. There we are. Good. So, is that fine? Did you see the change?
Yes.
So, good. So, I hope this doesn't sound arrogant or unplayful, but when I think about quantum gravity, I'm not thinking about it as an intellectual problem. I'm really thinking about it as, how the hell does the thing work? How does the universe work such that gravity is coupled to quantum materials and it all makes sense? So I think I see a unified solution to all of the big problems in physics. I don't want, there may be an intellectual solution to quantum gravity independent of unification with matter, but that's not what I'm ultimately interested in. So what I want to imagine that we're going to do here soon is find a solution to all of the issues. And for me, all the issues are open. So I think the foundational issues of quantum theory are completely open in my book. There's no approach that works. And therefore, we have to find a way to solve all the foundational problems of quantum mechanics, however silly that may sound, simultaneously with the problems of quantum gravity, simultaneously with the problems of unification. And I'm going to go for it, as they say, and say also with the issues of concerning consciousness and qualia. I want to get a solution to all of those. And I'm not planning to have one to show you today, but I have one to discuss that presents one way we might go about it. Okay? Any questions? Okay. So nobody's asking, how are you going to do that? How could you imagine? Well, this is what we're going to do. We're going to take, when we come to quantum gravity, we have a bunch of different choices to make. Is time fundamental or not? Is space emergent or not? Is space-time continuous or made up of little chunks? How do the little chunks put together? So we're going to take as a correct model of how space-time and the quantum fit together to be a causal set, more particularly an energetic causal set. I'll be describing what that means if you don't know it. We're also going to take, and this will ultimately matter, it's not going to come in too much to what I talk about today, but I've been studying for a long time the hypothesis that the laws don't have a single explanation. It's not, this is why the standard model is the result of evolution over long periods of time. And it's going to be important for how we solve the other problem, that we solve in such a way that laws can evolve. Okay, so this is kind of my working outline. Then, in terms of what approach do I take to nature overall, I'm a naturalist. So that means that I believe that there is a way the world is. So I'm interested in the way to understand quantum geometry and geometry that lets me be a naturalist. That eventually, when it comes to just gravity, that means I want a hidden variable theory. And that sounds old-fashioned. It's the only choice. And I'll depend in the discussion. But I want a particular kind of hidden variable theory, which I call a relational hidden variable theory. That's one where the degrees of freedom are relational. And I'll say on the next slide what exactly I mean by that. And the kind of space-time theory I'm building it around again is an energetic causal set. And when I come, which I hope to have at least a few minutes for, how I aim to think about incorporating mind and qualia in the picture, I'm going to be thinking about a kind of restricted panpsychism. It's not a new idea, but I have maybe some new angles on it. Then everything is going to go through a limited statistical analysis. That is, we're going to be doing ordinary statistical mechanics on the above issues. And that what will come out is hidden variables with everything we need them to come out to. And what will come out is particularly hidden variables with a particular kind of kinetic energy and a particular kind of a particular kind of so this is done. What is the kind of energy that you learn about in school that's not kinetic and potential energy? A particular kind of potential energy, where the potential energy is tied to what's called the variety of the configuration. And the variety of the configuration is a quantity that we invented a long time ago with Julian Barber. And so that's the sort of picture of the whole thing. And I think I'll skip the next one. So if I go by principles, I'm a naturalist and I'm a relationalist. And I'm the kind of relationalist who Leibniz is close to. So I believe that the universe contains, that there's nothing in the universe except what is in the one single universe. I believe that the universe contains everything that is the case. I also believe that our universe is complex and that the complexity of the universe is a necessary thing to understand how it gives way to quantum mechanics. Okay. And these are ideas that started to come to my thinking about 30 years ago. And I published the first relational hidden variable theory in about 1983. And if we go on, there were a number that were investigated. We investigated eventually with coaching Marco Polo and Artem's since started off. Steve Adler had his own point of view. So that by the time we get into sort of 10, 20 years ago, the idea and the concept of relational hidden variable theories is well developed by a small number of people. But we have a good idea about what they involve, and we have a number of examples of which we can solve, and both exactly in some cases, and in terms of computer simulations in other cases, and we know how these things are working. Unfortunately, I'm not going to go further with that, but I'd be happy to another time. So that's one corner of the theory. That's the relationship to hidden variables, non-local hidden variable theories. Now, in fact, you shouldn't think that this is a description of things moving in space with other things on top of it. You should think that a relational hidden variable theory simply has no concept of space. We talk about non-locality. We have no concept of locality. We just have degrees of freedom. So the ontology, the basic ontology that we're talking about is one of what we call emergent energetic causal sets. Energetic causal set is a causal set, I'll tell you what that is in a minute, which has as fundamental variables energy on the causal links. A causal set is you can call it a category, it's a object made out of events which are tied together by causal relations. And in the original version, that was all they had. In our version, there is energy and momentum on the causal relations flowing from the event that the causal event started at to the event the causal set went to. So causal relations between events are transfers of energy from a causally earlier event to a causally later event. So there's no space, there is causation, and there is time. So we're left with a universe that out of all of space, time just has time, and time are a combination. You should think of time as kind of what time does is create a universe made out of causal events and processes. So if time is the activity of time, you can say is the continual creation of events from past events to future events. And we'll have some more pictures of that. So this is a formulation which very much is not symmetric under time reversal. And that, I think, is the right thing to do. Now, a causal set, or an energetic causal set, grows from the past to the future, in inventing or constructing a present nearby. Now, what we mean by that is that the causal set, as it grows, what exists at a given moment of time is the present. The future simply doesn't yet exist. So the future is things that might have happened or might still happen, but haven't yet. And the past are things that have already happened and are left behind. And to make that precise, we say that when the causal set is growing, what time constructs is the future, the next future event. The past is already gone. The past is no influence on things further to the past. So we simply say that the past doesn't any longer act or exist. So the past may be thought of as gone. Now, Heisenberg talked about this way of thinking about quantum mechanics and emphasized that what it meant is that the quantum formula, the Hilbert space, the basis elements, and so forth, were descriptions of the future. And they were probabilistic descriptions of the future that allow us to guess or predict to some degree what will happen in the future. That is, what events will pass from the future to the past. But there is no quantum notion of past. When something has happened, it's happened. And it either plays any future role, nor plays any role in the past, and therefore there is no reason to really speak of it after that. Now, in the past, there is an important structure, which is the following. You call it the past of an event, and you take an event and consider all the events at one time in the causal past. That's a causal neighborhood, which is one step back in the past from the event you're starting with. And then you can go one step more and one step more and so forth. And you're building a structure, which is sort of half the causal structure, defined with respect to one event. And that is like the past light cone of your event or past let's say, past light code. And we'll call it, just to make things simple, we'll call that the past. And the past is going to be relative to the present events. The one thing that we want to say is exists, and truth statements about have truth values. If you want to say what is real in this formulation of quantum mechanics, what is real momentarily is the past of each event. So it's the past that is real, and you want to measure and make predictions about, and so forth. Okay. I have a little bit more here. Time is a process which continually brings into being novel events. By doing so, time transforms what was a moment ago future events, and thus potentially events, into present events, which then quickly become past events. By the way, I'm using a time vocabulary, to discuss space and time and the past and the future. And I'm speaking as if this is real because I believe it's real, because I think that this is the right way to think about space and time as a continually growing set of distinctions among events. And that's it. You see what I mean? There's nothing else except this growing present set, which used to be something we just conjectured about when it was in the present, in the future, and quickly passes through the present and exists briefly, and then is gone into the past. So that's our view of the universe. That's our view of what is going on. And it's a rather stark one, you see what I mean. The view of an event is what that event knows to its causal past, by information that it gets from being part of the backwards light cone. Now, that is the fundamental structure. Everything else is emergent. Emergent properties are properties that are left behind as this process of constructing the universe passes through it. And we want to think that these emergent properties we can speak about because they're related to time, which doesn't change after that point. And we particularly want to talk about space as an emergent property in this way. Space-time, we'll talk about particles as emergent in this way, and fields, but not much else. Any questions? Otherwise, I'll keep going. This is a little bit more about that, but let me just emphasize the key points here. This is a view of the universe in which the present is always moving and changing. And it does so by, at each moment, some small number of present events become related to each other because they become the parents of just created events. And it's that continual creation that makes it easy to distinguish the present events from the just past events, from the events which may be just to come in the future. And because of this, and we don't have time to analyze it more, but because of it, there's a rather tight control over the kinds of structures that you can build in this context. In other words, ordinary causal sets are very loose, and this is very little that constrains their structure. These are very constrained. And in particular, these are constrained by conservation laws because the conservation of energy and momentum passing through an event that originally exists as part of the energy momentum of other events passed to it. That energy momentum is passed to this particular event's energy momentum. And those are then passed to the future. and there are conservation laws governing that. And the conservation, those conservation laws are primarily the drivers of evolution. You may know that in gauge theories generally, and this is a gauge theory I'm telling you about, the gauge transformations are generated by the symmetries and vice versa. So all that structure relating symmetries to gauge transformations is locked into this machine, we can call it, as it goes about its business, constructing the future. Now, there's a lot of freedom. There are not deterministic evolution laws. There are a lot of things that could be the next step that are lawful, and that's why there's gauge invariance. So this is again just a picture of the structure around a vertex in an energetic causal set. We have a vertex. It has only the structure we've given it, but the P's to the Q's is a conserved transformation, and they're the same for the next. Let me go. These things make all kinds of interesting structures as they grow, and maybe we can talk about that. Yeah. So this is a summary. What's fundamental in our ontology is events, the causal relation between events, and the structures of past spaces and so forth that are created. From these fundamental constructions, these fundamental relations, and let me emphasize this, we sometimes get the emergence of space. Sometimes we do, and sometimes we don't. Let me now explain them, because there are various claims going on, and some of them are very interesting, that people have constructions where space emerges as the system develops. We definitely have a dynamical process from which space emerges by being left behind. And whether you get space to emerge works something like the following. So this is the light column that we're calling. This is the past of some of that. But let me skip that. Let's talk about how we set up a path integral, which and the path integral as the product over events of amplitude. At the events, we fix the incoming and outgoing sums, and we construct a probability. This is all very conventional. When we're done, we have a path integral controlling the construction and the application of the conservation laws through the system. And we have a dynamically constructed space-time which successfully conserves a certain number of quantities. Let me emphasize that this is the complete definition of it. This is quantum gravity, whatever it makes. It's whatever replaces quantum relativity. And notice that there is no H bar, there's no space-time, there's no commutation relations, there's no uncertainty principle, because we're only integrating over I forgot to say one last important thing. The way that we implement the delta functions, which generate the conservation laws, are by an integral, by the standard delta function conservation. The Lagrange multiplier that expresses that conservation law or constraint becomes the variable that describes space. So there's a close interplay between the variables which are no longer nothing else but Lagrange multipliers and the sort of bones of space. And because of that, our path integral only has half the things that the usual path integrals have. And because of that, there's no H bar in the computation of H's. All these things emerge, and we show in detail how they emerge. Then there's a little bit more to say. What about particle dynamics? And we, using the same methods, let me go ahead. Same. Notice that the path integral is the product of delta function integrals. So it's what the general relativists would call a pure constraint theory. There's nothing in the theory but the conservation of gauge principles. But the Z's are exactly what you need to label the coordinates of space, time. They are invented in this process. So this is the detail. Massive. I think I must be close to end time now. Well, I'll keep talking until somebody tells me not to. Here's how particle trajectories emerge. For every two Z's, which are the Lagrange multipliers that are part of enforcing the momentum conservation, it takes you from the ith node to the kth node. There's a degree of freedom, which is called P, okay? And that is conserved around each vertex. And so you get, when you vary the A's, which are the Lagrange multipliers, and also the Z's, which are the positions of the ends of the Lagrange multipliers, we get, we integrate over alternatively linear and quadratic equations. And we get from that the structure of edges connecting nodes. And these structures from edge connecting nodes produce, in the case that there had been two nodes, two edges per node, gives you a structure which you can just draw and put together on your blackboard. And that structure either is strong enough to hold a space-time together, in which case you get a space-time, kind of discrete space-time emerging from your process, or it's not. So you get here clean criteria for either constructing a space-time or not. If you don't construct a space-time, you construct some sloppy or inconsistent set of relations, but you don't get anything classical. So you continue growing your space-time. And let me just finish. In the end, if you constructed a consistent large structure, you constructed a discrete approximation to a Lorentzian space-time. Well, and that's fine. Then you have constructed space-time and shown how it recovers from the dynamic relations of all the conservation thought. Or you haven't, in which case you lack your quantum theory is not strong enough to bring to life a completely consistent causal structure, and you fail to create a space-time. But I think that's the way it has to be if we're going to claim that a theory constructs or gives a construction of an emergence of space, because it has to be contingent whether space is constructed and emerges or not. Otherwise, we would just be making some kind of fake theory and holding it together with nails and hammers and so forth. So there's a lot more to say, and then I'll stop here and wait for more time. Thank you very much.
Thank you. And we have comments from Emilia, and then we'll open up for general discussion.
So first of all, let me thank you, the organizers, for allowing me to comment on Professor Smolin. I'm very much honored to meet you, though on Zoom.
Thank you.
So let me start by saying that a very famous post-structuralist philosopher named Gilles Deleuze wrote that, talking about Leibniz, that about principles, he is undoubtedly the only philosopher who does not tire of inventing them. He invents them with pleasure and enthusiasm, to then brandish them as weapons. And at the same time, he plays with principles, multiplies their formulas, varies their relationships, and is obsessed with the idea of proving them. So it should come as no surprise that the fact that Lee Smolin, one of the most recognized and fascinating contemporary physicists working on quantum gravity, combines his devotion to the philosopher Leibniz with a renewed love for principles, which in his understanding are meant to somehow allow a new revolution in physics. So the main idea, as far as I can understand, is overall enterprise is that the most insidious aspect, the most insidious flaw of model is that of models in general, is that they guarantee results, in that they somehow limit the number of entities in the field and restrict the characteristics that can be assessed. And the point is that to see it in Smolin's eyes is that models incorporate ideas we already have about the world, and in this sense, they limit the possibility of revising them. So this is why he believes that in order to perform a true revolution in physics, we need to start from scratch by redefining what principles should be somehow endorsed. And so in his extremely fascinating works, he has tried to outline which may be fruitful principles to put in the field of trying to look for a more complete theory. And these are, we will not go through it, I will not be commenting on them, but essentially, of course, background independence, the idea of relationality, the idea of causal completeness, reciprocity, and then the most Leibnizian of principles, which is the principle of identity of indiscernibles. And so the idea is that by embracing this set of principles, we may try to somehow redefine what is physics, and in particular, what physics is meant to do in the cosmological sector. So the general idea is that against what he describes as timeless naturalism, and moved by a sort of what we may call a sort of horror of the block view, as is typically described in the context of metaphysics, we should rather embrace a form of temporal naturalism, which somehow adds as its core point, starting point, this idea of time being fundamental. So provided that I do share much of these ideas and the idea of starting from scratch, from principles, I just would like to ask very short and maybe clarificatory questions to Professor Smolin. And the first is, why do you think that temporal naturalism should fare better than timeless naturalism in order to account for our experience, especially if you want to embrace that form of restricted panpsychism you were speaking about? And why should I choose time over space in order to do that? And why should I not conceive them both as being emergent? The second aspect is the one concerning one of the principles he's advocating, namely the one of background independence. And so there seems to be a sort of tension between these desire and the fact that we are taking time to be fundamental. And so I would like to hear more about why you think that time being fundamental is still compatible with this principle, and whether that has to do with this idea of time being characterized by its activity, and so the coming into being, which is again is codified by this idea of the horror of the block. And in particular, why this should be useful in the cosmological sector. And then I would like to ask you, I have a bunch of questions, but maybe I will leave them for later on. And yeah, my last question is the one concerning this very interesting set of theories that he's been developing with collaborators concerning energetic causal set theories, and in particular the connection with the idea of the principle of maximal variety that he's been developing with Barbour. And so again, what I would like to hear is, if in his account every event is to be portrayed as unique, and this uniqueness is granted precisely by temporality or causality, how can different events in the end interact, provided that each of them is unique, and provided that the likelihood for them to interact is precisely contingent on the similarity of their views? Thank you.
Is that all?
All right.
Sorry. I think that some of the things that you point out are genuine weaknesses in the construction. I'll deal with those that I'm aware of. And of course, I forgot to say and emphasize that this is collective or joint work. And some of my collaborators, who are fabulous thinkers, are Roberto Under, who really is the most radical thinker I know about these issues, and also Marina Cortez and Clelia Verde were essential in the whole project of inventing the particular structures that we use. And so I should absolutely start with talking about their influence. If you read Roberto, you see he is absolutely onto the issue that you mentioned. And indeed, he wants to make it his central cause. The central cause is not only laws that continually evolve, but laws whose he's interested in the change of the change, as he calls it. So Roberto, I wish I eventually grow up to be as consistent a thinker as I think he is motivated centrally by your essential question. And I think what he has in mind is something where we're going to have principles of change which are continually changing. And we don't have to answer what he calls the meta law problem. The meta law problem is the problem of if laws evolve, then what governs their evolution? And it's really, I think, his whole motivation to find interesting and important solutions to that, metaphysically important. And I'm certainly not a metaphysician, but I believe I'm in the presence of one when I talk with him. I hope that helps.
Yeah, definitely. Thank you.
Well, I would say let's make this a short series of short exchanges rather than my appearing to be brilliant, which I'm certainly not in this context. So go ahead.
Okay. To ask other questions? Oh yes, I have a bunch of questions. Yeah, at a certain point, I don't remember in which paper, you were discussing the fact that, because this I think is something that is again related to the second question I asked, namely the one concerning background independence, and how is this compatible with the idea of time being fundamental? And I was wondering whether you could expand a bit on why you would distinguish your understanding of time, or what is typically regarded in the community of metaphysicians as a form of presentism. And I guess that the role that you were mentioning concerning the change of change, or the meta law concerning the evolution of laws, has something to do with that. And so I was wondering whether there's something else you could add on this.
Well, I would just say that the other side of this worry about meta laws and so forth, any meta laws, for me is discussed mostly with Claudia Verde. And I think that in that direction, she is a more interesting and maybe deeper thinker than I am. I will answer your question, but I hope it doesn't sound trivial. If you think of Fotini Marcopulo used to say that you allow time to exist and space not to, because to have it the other way around would be incredibly boring. That is, evolving the laws which govern changes in time turn out to offer more opportunities, many more opportunities. So understand in a deeper way what the universe is trying to do. And, the evolving of and this is reflected in the structure of the differential equations. That is, it's very important that the equations which evolve time are third order, whereas the equations which evolve space are ordinary second order differential equations. And therefore, you, in some sense, can't invent anything interesting by what are essentially linear laws. And so it's a thing that I think a person has to spend a long time contemplating the structure of the laws of general relativity and really trying to understand what's the difference between the diffeomorphism of space-time and of time, or a diffeomorphism purely in space. And the fact that the second kind is governed by just a first order differential equation, whereas the second is governed by a second order differential equation, is all the difference between being able to generate indefinitely new structures, new processes. I barely touch the surface of what you asked, which is that give you something to go with.
Right. Okay. Thank you. Thank you so much. And another question that I have is, as we started saying, your general enterprise was meant to somehow favor what you call temporal naturalism against timeless naturalism. And in a recent paper, you write that embracing temporal naturalism should provide fruitful insights also in the cosmological sector, and in particular for fine-tuning problems such as why these laws, why these initial conditions, and so on. And so again, I was wondering if you could expand a bit on this. So why would you take temporal naturalism to fare better than timeless naturalism?
I guess because my sense is that, I hope this doesn't sound too mystical, too odd. There are phenomena in nature which are extraordinary and surprising and will always be that way. And these are temporal phenomena. And there are other kinds of phenomena which will always be basically boring. And these are first order phenomena. And one sees this easily if one looks at the structure of the constrained differential equations. One sees that there is a constraint that drives mystery or novelty, and that is the Hamiltonian constraint. And there's a constraint that generates repetition and just do it over again. And I'm sorry I'm not maybe expressing this well, but It's especially striking if you go down to a formulation in terms of matrices. Because when there's a formulation in terms of matrices, you have a matrix equation, which is cubic, driving matrix equations, which are linear. And you see that there's nothing similar about them. Even in this, of course, it has to do with the equations of motion that are chaotic, are cubic, or are quadratic equations, whereas the equations that drive simple equations are just linear equations driven by cubic, just linear equations. Do you get something of what I'm referring to there?
Oh, sorry, I didn't understand your last phrase.
Do you see? I mean, it took me a long time to appreciate this, and it took me working for years on a project that maybe you haven't done yet, which is how to make an infinite, how to express the laws of general relativity in the form of infinite matrix equations.
That I don't know of, but I'd be interested in reading it.
Yes, well, thank you.
Thank you. If I can, I just have one last question. Yeah, sorry. It's a unique opportunity. So, yeah, as I was saying, with this energetic causal set theory, you look to be interested in trying to connect this idea of this notion of variety that you have been defining with together with Barber, and to connect it with the idea of potential. And again, in another paper, you want to show the relation between this principle of maximal variety and some sector in which you get Bohm's quantum potential. Mm-hmm. And so I was wondering if you could expand on that, as I have a particular passion for Bohm's works. And so
yes, me too.
Love to.
Me too. And I was floored when I realized that the two equations were related to each other. Totally floored, because until you put them in the right set of equations, there doesn't seem to be any hint that Bohm's mechanics laws are related to Julian's notion of variety. But once you see it, it's unforgivable. So, by the way, it would be lovely to be able to work more with Julian. And I'm afraid that we've let our differences come too much between us. And this is true. I mean, most of my friends in science are relationalists, and most of them are, in my view, letting the difference between temporal and non-temporal relationalism keep us from working together more. I think that's a shame.
Great. Thank you. Thank you so much.
Thank you.
Okay, the floor is open for other questions and comments. I'll go ahead and ask one myself. Lee, this isn't something you explicitly addressed, but you might have done so in other work. I'm curious how the perspective of energetic causal sets relates to singularity resolution. So is there a sense in which you avoid or change the account of the initial singularity in this approach?
That's a new idea to me, Sonia. But it sounds, certainly the idea that if you want, I think what you're supposed to do if you're a smart general relativist, which I'm not, is mod out by all the linear equations and look at the equations that you're left with, which somehow drive real structure. And I think that getting rid of the linear equations and studying the remaining quadratic equations is, again, is something you only see in a certain coordinate system. And this, one of those coordinates where we have this, I'm not saying the key thing. The key thing is that general relativity, our study of general relativity was for decades, in my view, held back because we didn't know about Roger Penrose's cubic variables. And when you understand general relativity in terms of these cubic variables, you see that the action can be written to be purely cubic. And the equations of motion become purely quadratic. And that kind of carves open the importance of the relations between those mathematical structures and the difference between what quadratic and cubic equations can generate. And I just haven't thought about what role this plays with singularities, but it clearly could.
Thank you. I think Sakshi, sorry.
Hi, Professor Smolin. Thank you very much for coming today and sharing your life's work. I have a question about something that you mention in a chapter on temporal relationalism that I think is related to what you spoke about today. And I'm curious whether there's a connection with your view on black hole physics. So it seems to me that you treat momentum space as fundamental in part because it allows you to admit of infinite degrees of freedom, especially if you treat it as a continuum. And if I misunderstood what you wrote about that, I'd appreciate clarification. But it seems very important to you to not treat nature digitally, like a computer, that we want to admit of, novelty,
Yes.
and boundless possibilities. And I was wondering if that's the reason that you favor a non-holographic interpretation of black hole entropy, in which it can have unbounded interior entropy, where the Bekenstein-Hawking bound, just describes a subsystem, presumably the horizon, or if there are other reasons that you are driven in that direction.
Well, I think I'm driven by the views I have about black holes because they're eventually turned out to be the right ones, if that isn't too arrogant to say. I think that the argument over black hole entropy has been going on for a long, long time. And I certainly, for years, went along with mainstream, and it was Bob Wald and Dale Unruh, among other people, who just reminded us that it was really came from Roger to Bill to the rest of us to remind us what Roger really had said about the questions of, first of all, there's this equation that everybody shows, which shows the location of the horizon, which is just wrong. And it's wrongly implemented and wrongly argued for. And I could explain that sometime with more time. And the relation or the limitation that Bekenstein discovered is a relationship between fluxes of energy and information. It doesn't say, and it wouldn't say, that there's a limitation on the amount of information that can be inside of a black hole horizon. I think that was just a misimplementation, and I'm pretty sure that Carlo agrees with me on this. And once you reinterpret the equations that come out of Bekenstein's analysis, they are limitations on flux or flow of energy and information, and they're very useful and very important, but they don't imply anything like what they're said to imply. And I think that's just an issue. I think some of our friends have been a little bit too sloppy, frankly.
Well, thank you. It helps actually to hear how you depart even from other physicists like Rovelli, who ultimately agree that black hole interiors should have, unbounded states. So thank you very much.
Let me just pause. Let me just give some appreciation to Carlo, because I didn't think that there was much to find in studying black holes. And he and Francesca and their friends really have, I think, pointed the way to black holes being an important question. So thank you.
Okay, Sean and then Sam. So go ahead, Sean.
Hi, Lee.
Hi.
What a pleasure to be able to hear you talk again.
Yeah.
I wanted to pick up on your point about the difference between time and space. You pointed out that, the Hamiltonian constraint equations are second order and the diff constraint ones are first. That's always been interesting to me too. But it's not just that they're any old second order, they're actually elliptic, which means that they're well defined as a Cauchy problem. Because you could always just slice the space into time-like hypersurfaces, and then the second order Hamiltonian constraint would be radial, but that would be hyperbolic, and it wouldn't be well defined as a Cauchy problem. It'd be a boundary. So the interesting thing is that it doesn't matter what you do, there is some kind of causal structure there in GR. And I thought that was interesting that the program you set up today was taking causality very seriously as well. Is that an accident, or is that part of your intuition, or an accidental accident?
I don't know. I don't know.
Okay.
It was you guys who, to me, pointed out the importance of looking at the trading the space-time constraint for the, what's it called, the conformal invariance. But I don't recall any thinking about those things as if they were connected.
That's the thing we struggled with, is getting the causality, because in the conformal geometry, that causality looks really ugly. Anyway,
Yes.
yeah.
Sam, and then, go ahead.
Hi, Professor Smolin. Thank you again for your talk. I just want to follow up something that Emilia was talking about, because I can see that you are committed to background independence and relationalism and the principle of sufficient reason, how all those things fit together. And I can see clearly the argument you make that to do with the order of time and space. But I struggle to see how you can have the two things together. Either you have, for very good reasons, treating time differently, or you have a relationalism which is totally principled and in which everything is, or a vision in which everything is relational and totally background independent. And I struggle to see how the two can kind of go together in that way.
So I don't see it. Can you explain why they don't go together?
Just because it seems as though, sorry, I'm trying not to shake. I'm very nervous. I'm
much more nervous. I'm much more nervous than you are. I can.
I struggle to believe that.
Well, come over here to this side of the screen.
Because it seems at the moment when you don't treat time when you have a relationalism which isn't timeless, you're treating time differently, and by doing so, your theory is less background independent. And I can see that there are separate, very, very good reasons that you might give for doing that. But it seems like if you have a wholly principle of sufficient reason, background independent relationalism, it seems like putting time into the background. Or I'm sorry, you probably wouldn't be putting time into the background.
Yeah, I see. No, I don't treat time as similar to space because they both are governed by constraints. We somehow avoid taking that term, if that's where you're going.
Sorry, could you say that again?
So yes, the way that I understand the way that the equations fit together, no matter, even if you make a 3+1 split, as dramatic as you can possibly do it, the role of the generation of change under the time coordinate is very different than the role of the generation of change under the spatial coordinates.
Okay, am I? And that makes perfect sense to me. It just seems as if you're truly committed to completely principled system building up in a sort of foundational and way, that it would seem more relational, more relationalist, more background independent, for there not to be that distinction at the most fundamental level, even if there are very, very good reasons for it coming out.
Let me see.
Maybe not.
But it would be nice to discuss that sometime with more time. I see what you mean, but I don't think so. And let me think about it, and maybe we can talk sometime.
Thank you.
Thank you very much.
Thanks, Sam. It's Francesca has a question now.
No, sorry, I needed to apologize because I had a very spontaneous reaction to Saximi before. Just wanted to clarify that the idea with the black hole physics. So what a community reacting to holography is saying is that you are not bounded in the number of states by the horizon as you have in holography, but it's not that there is no bounds to the internal states. So you have a very large volume inside, but this volume is finite.
Yes, sorry. I realize that there's divergence. I've read some people that do believe it's unbounded and some that it's much larger than Bekenstein-Hawking entropy, but can still be bounded. So I apologize if I put some people in the wrong side of that. Yeah.
It's multidimensional, of course. Yeah.
Anyway, I'm sorry I missed the whole discussion between you because I am only looking at a blank screen. But I can see that would be troublesome. I was going to say something. Oh, I never got to say that. Look, I have very good friends who have spent many, many, many hours on the information problem in ADS space. And I just don't get it. The world is not ADS. It's not in any sense close to ADS. And I don't understand why people continue to study a model which is not relevant to nature. Maybe that's my problem.
Yes, Dominic and then Nick.
If I could try to be devil's advocate for that, I mean, if we want to have a complete theory of black hole thermodynamics, we're going to need some sort of definition of equilibrium with, at least for the zeroth law. In order to have that, we need to be able to bring a black hole into thermal equilibrium with radiation, which requires containing that radiation somehow so it doesn't go off to infinity. And ADS is a good way of constructing that because it basically essentially puts a black hole in a box. And so we can get now we can analyze and understand black hole thermodynamics with these models, despite them, and then bring that over to realistic models of our space-time.
I think we were discussing this a few days ago. Is that right? Over because anyway, I hope we were, because I don't think, with enormous respect, I don't think you're right about that. I don't think that black holes are ever close to equilibrium, and I don't think that the concept of equilibrium in an ensemble is very useful or relevant for black holes. And I'm happy to discuss that in a great deal sometime later. And I think we were a few days ago discussing that in the hallway at Plymouth. Am I wrong?
Nick, go ahead.
Thank you, Lee, for the great talk, and it is nice to see you on Zoom. So this is a kind of quite general question, and I think when I've heard you speak, you often kind of address this, but could you just talk a little bit about the relationship between the energetic causal set theory and what's coming out of that, and, you know, approaches to quantum gravity to which you've also, you know, contributed a lot, you know, namely string theory and loop quantum gravity. From what I understand, you don't necessarily see these as strict competitors, but there is some more positive relation between them, or is this really an alternative?
I think that my sympathies for string theory are kind of moving on, and that's because. But it may be that I have too many things I want to think about, but I don't see the persistent problems with string theory as moving towards any resolution that will give us real knowledge of what's going on. And my sympathies for loop quantum gravity are a bit higher, but but I also don't believe that loop quantum gravity will be the fundamental theory. Essentially, my standards have gone high, I guess, has gone higher. And some of it is I'm tired of listening to people talk about alien space. I think that it's I've said enough.
So the question is also about the sort of logical relation between those different theories. So you really do see this as largely as an alternative, and then you're describing your sort of, you know, credences towards towards them, or is there some possibility of cohabitation here?
You know, I've always been a big advocate of cohabitation. Now there are a lot of people advocating it. There's a lot of conferences in the physics world about at least in perimeter and a few places like that, about we should all cohabitate with each other. But I think what's really happened is that string theory has collapsed. It's not generating any new ideas, apart from the ideas having to do with boundaries, which in my understanding really came from relativity. And people are looking for somewhere to go. And cohabitation is a nice thing for people who used to be string theorists. And on a social level, I like that. But I think that I still think that they don't get it. I think that when people come to our world from string theory or something, they don't. It's so rare that somebody is able to just quote correctly the first 4 or 5 results of loop quantum gravity that led us to see it could be important. And you can't. So enough said. But maybe I'm just in a bad mood. I don't know.
Oh, that's good.
Okay, so I think this is an appropriate moment to thank Lee and thank all of you for the great
Thank
discussion.
you very much.
Yeah.
Thank you.
Look and study quantum gravity because it's philosophically so rich, but hopefully there will also be the occasional physicist who will read what we've written and maybe, ask novel questions about their own approaches or other approaches. So I think in that area, there is a very straightforward connection and relationship between the two fields. And I feel grateful for the fact that so many physicists working in quantum gravity are very open to engaging with philosophers. I do doubt, however, that this is generally the case for physics. I mean, all of physics. There's many other areas, of course, of physics where I think there is very little interest or interaction with philosophers. And that's probably okay because they don't need to all engage with the foundational philosophical questions. But of course, that's why I work in the foundations of quantum gravity.
So I think Francesca had a point on this.
Yeah, just to follow up a quick comment on this, because so the question was about creativity. And of course, you are a philosopher and you ask about the impact of philosophy on doing science. But I think it's important to recognize that we scientists as human beings, we nourish ourselves with everything. So it's not just philosophy, it's about the place in which we are grown, the social, economical background that we have, the gender that we have, the possible neurodiversity that we experience, and so on and so forth. So we really need to recognize all these multidimensional aspects that all converge into creativity. And playing music or being an artist, all of course has an impact in the way in which you think, and therefore in the possible solutions that you see for the scientific questions that you address. But said so, I will also say that people who don't engage and don't think about this, they of course have a very precise philosophical position, and also a very precise sociological position, and also a very precise historical position, because this is something that is true in a very specific place, in a very specific time, but is that it has not always been true, and maybe, hopefully, we are going towards a new phase.
So I have Emilia and then Charlotte.
So I feel guilty in a way because I was just starting to ask questions on specific, on two specific presentations, and then the conversation turned out to be probably even more interesting. But I will do them if it's okay. So the first is for the presentation of Shangri, and I was wondering if you could say something more about this idea of the algebra of observables being contingent context dependent, and I was wondering whether you could say something more about it, because I don't know about it.
Yeah. I mean, there's a lot to say. I think that one of the things I had in mind maybe is like the Galileo ship example. So if you imagine being in a ship with all the things closed, you can treat Galileo invariance as Galilean invariance is like a gauge symmetry inside that ship. So if I'm trying to model how water is dropping in the ship and how balls are moving, I can do that, and I can treat the Galilean invariance as a gauge symmetry because it doesn't matter. But the second I open the window and I see the shore outside, then I have a new set of, I become coupled to the outside world. There are now relational degrees of freedom between the ship and the shore that are going to be changed under a Galilean transformation of the ship. The thing that used to be a gauge symmetry of my target system is now no longer a gauge symmetry of the new system. That's because the target system has changed. So that kind of illustrates the point that like you could have the same representations, you can have the same theory, and but because the target system changes, you now no longer have the same gauge symmetries. And so that's kind of what I had in mind. And I know there's a big literature about this, and I think it gets really complicated. And so I prefer to just take this simple approach where I say, okay, I have representations of the world and I have target systems. And gauge symmetries are particular relationships between those two things. So if you change the target system, then you also change the gauge symmetries. And then just keep it at that.
So you want to keep yourself agnostic with respect on what you would take to from these on the nature of the algebra observables, on the nature of observables.
That's right. But I don't want to be agnostic. Once you identify the gauge symmetries, I don't want to be agnostic with regards to how you treat that observable algebra in your theory. So when you say, I have this observable algebra, this is what it is, then I think the equations of motion should be well posed on that space and nothing more and nothing less. And I also don't want to be agnostic about the measures that you want to use to count possibilities, things like that. But yeah.
Okay, thanks.
Yeah.
Yeah, Ken? Okay. And so the second question concerns Luca's talk. And I was just wondering, I know this is all very complicated and like in the making, but when you were discussing the mean field approximation for early times, so what do you expect? How do you expect to proceed beyond this mean field approximation? And what's your understanding so far on the way which we should proceed in that context?
Yeah, so that's a hard question. There are two ways in which one can try to do that. One is really doing the full computation of the partition function with all the difficulties associated to that I mentioned before. The other way would be to kind of do what is done in condensed matter physics again. So going beyond what would be the Gross-Pitayevsky equation and consider again Gaussian fluctuations around the mean field, but these Gaussian fluctuations are now full quantum fields. So you would have your operators for these fluctuations, and you would compute Bogoliubov transformation, study all the possible spectrum of all the quasi-particles that could emerge from that. So really following the condensed matter procedure. And we did start looking at that, but yeah, there's not a lot of literature yet. So it's really a work in progress, as you said. But it's challenging.
Yeah, sorry, but when you speak about the second, like to move in analogy with condensed matter physics, do you expect these quantum Gaussian fluctuations to be in the pre-geometric regime already?
Yeah, in a sense that they are. So in this, I do believe that these are part of the pre-geometric sector, in the sense that you're actually studying operators that live in the full theory, so quantum fluctuations in the full theory. So in that sense, there's no like indication that this would be part of a continuum phase. But on the other hand, you're kind of expanding around the mean field. So somehow you have a background which is homogeneous, and then homogeneous. It's proto-geometric, and then you're considering fluctuations which are pre-geometric on top of that, and you're trying to understand what's the interplay between the two, and that's not trivial, because like the analysis that we did, and that was just a really simple first step, again followed what is done in condensed matter. But to do that, we had to resort to a Hamiltonian formulation to do the standard Bogoliubov analysis. And the Hamiltonian formulation in general is not trivial to obtain from the group field theory, unless you assume that the group field theory is deparameterizable, which is something that is in general is not the case. So you should have a way to precisely define a quantum clock at the level of the quantum theory, And as I mentioned today, that is very complicated. So extracting a Hamiltonian out of that is very complicated as well. So you could postulate that somehow you're able to do that and then do the whole analysis, which is what we did. That, of course, can just be an idealization of what the whole story would look like if you wanted to do it properly.
And next we have Charlotte.
Thank you. I just wanted to go back to something that Francesca said this morning. So you said something like our positions in cosmology depend on our interpretation of quantum mechanics. And I think that this is true and also super interesting. And I think this is important for like a host of issues, actually, like metaphysical, ontological issues, for instance, about how we conceive the role of the wave function, if there is a universal wave function, about how we conceive like time, whether it's fundamental or whether we can get rid of it. And again, about how we conceive, like how we even define cosmology as the study of everything or study of the largest degrees of freedom, or whether we should rather think like thinking of describing the universe not in a like global way, but just like taking into consideration smaller degrees of freedom and like see how they evolve with respect to each other. So I was just wondering whether you could, I don't know, well, first of all, what people think about this, and if you could say like something more on like your preferred view on this.
I think my preferred view is very well known.
Yeah.
In the sense that, of course, I use relational quantum mechanics. And of course, relational quantum mechanics was born from Carlo. And Carlo also contributed to the beginning, together with Lee, of loop quantum gravity. So there is a natural convergence there, but I want also to say that most of the people doing loop quantum gravity and loop quantum cosmology as well don't necessarily use this framework of interpretation. In fact, most of the people, as you very well know, are not concerned with a particular interpretation. Then we can argue that they are using maybe Copenhagen or they are using some framework without being aware, but that's a different story. And then we are into sociology again. So yeah, and the reason, of course, why I like the relational framework for quantum mechanics is because among the different options that are on the table, it seems to me the one that is most compatible with the general relativity. But again, you also need an interpretation of the theory of gravity. And if you highlight in that case, again, the relationality as the common ground, it's kind of natural. So to me, the way in which I made sense of relationality in quantum mechanics was often making reference to the relationality that you have, for instance, in just in special relativity, the fact that you can have the different observers can have different accounts for the sequence of events in space-time. So once you have this notion digested, it doesn't seem so strange that the same could happen also with quantum mechanics. But then, so it's always a question. So one thing that has been highlighted by Carlo is the fact that you have different interpretations, and unless you move towards alternative theories that are not quantum mechanics anymore, that they predict something else, and maybe Lee would like to do that in the sense that he may think that quantum mechanics is not complete and we need something more fundamental. But if you stay with quantum mechanics, or even, so just to give you an example, so if you have, for instance, collapse theories, so there you really have different predictions. But as long as you stay with quantum mechanics, we have a set of predictions that keep on being verified, and all the interpretation have their own self-consistency. So how do you choose between different interpretations? Well, one possibility is to look at what is the interpretations that facilitate the jump towards a successive theory, for instance, a theory of quantum gravity. And from my perspective, of course, relational quantum mechanics has these functions, but it's something that actually we can only check a posteriori. So it's a bet that you make, and it's a bet that each researcher makes, and they make different bets. I should also say that I think we should be also a bit pragmatic and opportunistic in the sense that you may try different techniques that are available to you. So, for instance, I have no problem to use Bohmian mechanics if it allows me to do calculations. For instance, I don't buy the interpretation of Bohmian mechanics, but I am aware that there are a set of techniques that allow to write very good semi-classical equations. So I have absolutely no problem in using that framework if it allows me to go ahead. So I think this is the mindset also with respect to cosmology. So to check what is the step ahead that each interpretation allows us to take. Mike, you were nodding, so maybe you have something to add on this.
Yeah, I guess two parts of it. One, the some sense endorsement of pragmatism. So in philosophy of historical sciences, Curry's talked about it as methodological omnivory, just sort of a desperate, greedy reach for anything that is novel and interesting. That was one of the nods. The other one is this kind of move away from particular, say, interpretations of quantum mechanics and toward like total interpretive packages. So there's a certain, I think, arbitrariness with how we carve up conceptual space when we get laser focused in on, for instance, quantum interpretations. But really where they end up being interesting is when committing to one of them conjoined with a whole bunch of other theoretical commitments leads to some interesting feature of your theory now to exploit, possibly for empirical ends, possibly for further theoretical reasons. So at first pass, things like disagreement points amongst practitioners on particular axes like quantum interpretations, it's a good first pass for setting up the terms of the disagreement, for understanding where people could be talking past each other. But yeah, the real interesting action seems to come in when you explicitly couple those points of disagreement with a whole host of other interesting, diverse perspectives, a whole host of other yeses where other people go no. Those.
Okay, the floor is open either if anyone else wants to comment on Charlotte's question or if there's another line of questioning or another. So I'm looking at the graduate students in particular, or yeah, go ahead, Fabio.
So I actually have two kind of questions. The first is about what Emilia and Sean were just discussing. Just to be sure that I understand, you were saying, yeah, in the moment I somehow change my system, like for instance, opening my window, so I'm actually now consider a bigger systems, then the relational degrees of freedom and observables are changing. Is that your point, right?
Yeah. So.
Okay, but I mean, in principle, you can have similar thing, but even within the same system. So, for instance, one way I like to think about the presence of gauge symmetries, it's like, let's say you want to describe the systems purely intrinsically without any access to external relata, and that automatically introduces a sort of redundancy in your descriptions, which you can think of as the presence of a gauge redundancy. But in the very moment in which then you want to talk about subsystems of that total systems, and you want to describe them gauge invariantly, which, as Francesca was saying, actually means relationally, then even there, the algebras for the subsystems becomes dependent on how you describe them relationally. So even there, the notion of algebras or observables is kind of like changing, depending on how you describe them. And then he said the second think it's really just a broad question to the philosophers, actually, because when I was like reading around for commenting Luca's talk, it was one of the first time I was actually interfacing myself with some set of questions that, as Lucas was saying, we actually don't really face usually. And it was about indeed the notion what one means by emergence in the context of space-times and quantum gravity. And so, for instance, there was a distinction between, and I apologize if I don't use the correct terminology, but there was a distinction between intertheoretic emergence and I think ontological emergence. So, usually as physicists, we just think somehow that the attitude is, so we give physical meaning to things, but they comes out of the modeling of the phenomena we describe somehow. But as far as, so that would be, for instance, let's say, you call a phenomenon in that sense emergent from another if somehow your modeling of the phenomenon is kind of like deduced out of another or can be reduced to another. That, I think, is what you mean by intertheoretic emergence. I was wondering what actually means the other way around, like that the entity itself is kind of like emerging from another, because from a physicist point of view, at least to me, seems strange that the entity comes first of the modeling. So what's actually the point of view of the philosophers on this?
I want to highlight two philosophers in particular who have a book that deals with this issue. Nick and Chris.
But it's not finished yet, so we don't know.
We're eagerly waiting the outcomes, but I think either of you should take this question.
So I cannot speak for both of us. I just speak for myself. And Nick can then decide whether he agrees or not. But the way I think about this is that emergence is something that primarily arises when we theorize about the world, and we conceive of, in some sense, different levels of description or of theorizing, and that one thing at one level somehow must stand in a relationship both of dependence and independence from something else that's more fundamental than it. That is, it emerges from it, so there's a form in which it depends on it. It arises out of that. Without the more fundamental, it would not exist. Whereas it's also independent. That is, it's not just the more fundamental thing again. It seems to have some sort of novel behavior, some sort of autonomy, perhaps, that's not could not have been guessed from the fundamental level. Now, as I've already used now when I describe this, I'm going beyond the theory. I'm sort of assuming, like a naive realist, perhaps, that in my theories, I'm describing something. There is some structure out there in the world that I'm describing and that I'm referring to. So there could be a relationship between things, structures, as something in the world that is captured by the relationships, the theoretical relationships I'm trying to articulate. Now, there's many different forms and strengths of emergence. Some philosophers think when we speak of emergence, we mean thereby to exclude a reductive relationship, that somehow there's really something that's in a strong form independent of the fundamental thing, could not possibly be reduced in any way to the fundamental thing. When people think that, mind or mental activities or entities or life or something like that is emergent, they sometimes mean to say it can in no way be reduced to or derived from the more fundamental things. That's not how we are going to use the term in the book. So that much we already, I think, have established. We're going to have a much weaker use of emergence. which we take to be compatible with a way in which there is a reductive relationship, a relationship that can be scientifically studied, primarily mathematically, of course, with capturing the relationship between the two levels. But nevertheless, there's something novel and interesting at the emergent level. Like space-time, from structures in quantum gravity, which are completely non-spatial temporal, or at least prima facie not at all like a continuum geometry or anything like that. So that's an interesting question, how you can then have, nevertheless, something like a relativistic space-time, which at some scales is an extremely good description of that thing, which fundamentally is so completely different. And that gives us an interesting scientific and philosophical question of the relationship between these two levels. Now, I don't know for how much longer I should go on with lecturing, but maybe it's time to...
I believe Lee might want to join in the discussion. Is that right, Lee?
I might. Can you remind me what the question is?
What is emergence, I think, is the short form of the question.
And you just had these really smart people talking. I think emergence is really important. And I've become more open to more flexible notions of emergence as time goes on. And certainly not. I don't know. What's the question about emergence?
Maybe I can repeat it.
So, what question are you asking about emergence?
I mean, I was asking mainly whether one should think of emergence in a sense of like the way of modeling one. So, like, what comes first, the phenomenon themselves, independently of how we model them, or are we just talking about, let's say, the one model which is emergent from another? And because I was never thinking to the distinction between the two, so maybe having a more physics attitude that was identifying the two things, but apparently in philosophy seems to be a distinction between the two. And I was asking, what precisely is this distinction?
I think that the first, when emergence is useful, there's a first stage where it surprises you and you go, oh my God, could water and ice be different? And that's really surprising. And it takes, for a while, you're captured by this difference where you didn't think that, where you just maybe thought that these are always the same. And then you go through the third stage, perhaps, where you begin to dream that they could be, you can imagine that they're really different. But I think emergence, it's a hard problem, partly because in physics we're always trying to construct a difference between a limit and a very large number that limits to the infinite limit. And we're finding that that's important conceptually. And that's very hard to think about, at least for me. Does that help?
Yeah, that's helpful. Nick wanted to jump in on this as well.
Yeah, well, maybe I'll ramble on about it a bit as well. Maybe you don't want me to jump in, but I think to try and be a bit more specific about the question. I mean, because you're sort of asking how do philosophers kind of define and use these terms. I mean, I think I'm pretty bad at sort of holding on to exact meanings of terms, but what I think in philosophy is it's actually quite a mess what people mean by emergence, and there may be like two different dimensions that are sort of getting run across each other in the what you're saying. And I'm not at all sure that what we've done has sort of helped that mess, and probably the opposite as it sort of turns out. And people in different branches of philosophy have different sorts of ideas. But there's one distinction I think roughly would be, I would contrast the ontological with sort of epistemic rather than. So epistemic is something like, oh, we've coarse-grained, so we got some new degrees of freedom. but they're not really, that's a kind of reduction, right? They're sort of emergent. They weren't there in the original theory, say, but we've kind of blocked them together, and now we've got some. So that's very much a sort of intertheoretic kind of notion as well. Ontological is like what Chris was sort of talking about at the end, I think, where there just is no kind of total reduction relation. And in fact, I think, in the higher level theory, I can make changes that don't correspond to any changes in the lower level theory. So it's strictly non-dependent on it's just not fully determined by so that's one distinction. And you can see why it's epistemic, because I just don't quite know what's going on in the fine-grained details. Whereas, there really are new degrees of freedom that just aren't determined by that would be sort of epistemic versus ontological. There's another distinction, which perhaps I think is sort of more, I find also kind of very interesting in sort of intertheoretic. So I can sort of mathematically show how, my new degrees of freedom are related to sort of the old degrees of freedom. And I've got a kind of nice mathematical reduction, and I can explain in sort of mathematical terms. And I think so this is actually a kind of hot issue in philosophy of science, physics, or a certain corner of it at the moment. It seems a lot of the times that is just what physicists do, and that's kind of the end of the story. And then, you might come in and say, well, what was that lower level theory? What were the things it was talking about? And there's the higher level theory, and what are the things it's talking about? And how do those lower level things somehow kind of come together to be the top level things? But as soon as you're talking about sort of objects and things in that way, you're kind of moving away from mathematics, just from full mathematics. And now this is like a first order, second order logic. I have a domain of objects, and I'm kind of interested in logical identities between things. And so that's another kind of sense of ontological, the kind of entity. Anyway, but there's a sort of line of thought that if you start going in that direction, it's sort of a mistake. You should just stick at the level of the mathematics, and there's real problems with many of the philosophical problems come up when you try to somehow align the things at each level. So there's another distinction there between the sort of mathematical, thinking of a theory as mathematics, and thinking of a theory as mathematics plus a story about what that mathematics says there is.
Right. Can I just try? I think the mathematics issue is very deep and is fascinating. Is there something like there are two kinds of quantities that emerge from limits? There are the kind where it doesn't matter for anything whether you take that last step before you take t to infinity. So there's no important thing you learn by believing that the mathematics is an infinite set. You understand what I'm saying? Then there are systems where it does matter whether you take that last infinite step, which is actually a whole lot of steps. Not making any sense. In other words, if you look at a phase transition, if you don't take the variable to infinity that you're going to take, it's really nothing singular, there's really nothing different about the ontology of the last step. But if you take one more step, they become different domains and you can't easily go back. So is that the characterization? And if it is, how could that possibly happen?
Are you saying that because that's what you think, or I think Jeremy Butterfield and Chris Isham in their work have kind of thought about the importance of taking limits, and there's sort of a literature on exactly what that means, especially if we actually have a finite system. And are you thinking about that literature as well when you say that?
No, I wasn't smart enough to, but now I'm.
Cool. Yeah.
Mike, go ahead. And then, Luca. So Mike and then Luca. Sorry.
I just wanted to add a final ingredient in this because it's how one of the words you used when you were setting this up was maybe when you were unsure of what terms you wanted to use, you set up like the intertheory and then phenomena, like it's the phenomena first, or is that? And this was latched onto very much as like, oh yeah, you could be talking about some sort of epistemic or even just formal mathematical relations or ontic, the actual stuff that maybe there is some nice theoretical relations or maybe there just essentially isn't. But there's a third point where we can come in and say, theorists like working on the science are the ones doing the creating of phenomena. Certain kinds of phenomena are going to be relevant to immediate aims of research. So like earlier in my talk, there seems to be something very different about a quantum cosmos than a wooden table. Without getting into some commitment of, I think, wooden tables are out there in the world and they're sort of non-reductively emergent, so they're not going to be of interest in my quantum gravity, at least anytime soon. And yet, meanwhile, there's something that seems different. And I think the difference has to do with the aims, the pragmatics, the interests of the researchers. So another layer in this story to add to talk about when thinking about emergence is it the kind of emergence where we want to recast some familiar features of our world as standing in the right sort of limit relations to the kinds of questions we're asking in our research? Or is it the kind of familiar feature of the world that we just want to postpone, maybe even indefinitely, the task of spelling out how it's supposed to relate to our local, today's aims of research? And I think that pragmatic dimension enters into the emergence conversation as well. Even in the background of some philosophers talking about this sort of stuff. I think it's easier to see if you try to separate out questions of realism about what it is that we are learning about when we're doing the science from interesting questions about how these different things we're doing in science relate to each other.
May I just quickly comment on that?
Yes, go ahead, Fabio, and then Luca.
Sorry. No, just because now I was thinking, how much of this discussion actually depends on in which context you are discussing the notion of emergence. Namely, if I already have two physical phenomena that I can observe, then the problem of how do I model them and whether there is a relation between the two comes second. But for instance, in quantum gravity, it's exactly the opposite. Let's say we have observations somehow that we have established for GR, but for quantum gravity, there is still ongoing discussion, and we don't have yet clear net prediction that we have to look for. So there, in some sense, at least on half of the story, it's first the modeling that comes, and then maybe as you say, like the phenomenon itself. Is it a reasonable way of thinking of the whole mess, or am I messing even more?
I think I'm pretty happy with that. Yeah, this idea of we're going to get into the modeling first in this sort of intractable area that we're all confused about, and then we need to give enough structure to our inquiry there to be able to spell out what kinds of familiar features of the world we think are going to be relevant in it. So I think that sort of order dependence works fine with this further kind of emergence, the emergence of phenomena separate from emergence of separate from intertheory recovery, separate from what is in the world out there that may or may not, as an open question, be reducible.
Okay, I think Luca had one more comment on this line, and then Dominic has a separate question.
I was trying to understand the notion of ontological emergence as it was put before in physical terms. Maybe it doesn't make sense, but so as far as I understood, ontological emergence is You don't change. You change your parameters in your microscopic theories, and you essentially get basically the same result at the macroscopic level, at the emergent level. So could we rephrase that in physical terms by saying that there's a large universality class of models that lead you to the emergent phenomena? Does that make sense?
The way I was putting the distinction between, so I thought what you just said sounded more like epistemic to me. The ontological was, in that sense, is when, so this sort of strong emergence is what I kind of had in mind there, where the higher level degrees of freedom are not determined by the lower level ones.
The lower level ones are the.
So you can keep the lower level, there's some system and it must have, say has high, large scale degrees of freedom and fine-grained, degrees of freedom. But I can keep its fine-grained degrees of freedom the same, but vary these, and that's still possible, the higher level ones. So this is an ontological independence of the levels. So I think what you were saying was.
So what I was saying is, if I have a large class of microscopic models which lead to the same kind of macroscopic phenomena, wouldn't that be similar to ontologic emergence in the sense that, there is class of models, a large class of models that lead you to the same kind of emergent physics?
So a couple of things. So I'm not kind of thinking of a large class of, in the very simple picture I had in mind, I wasn't really thinking about a class of models. I was thinking about just coarse graining, like one class of models. So, it looks like I have these coarse-grained degrees of freedom that look like, that look like new ways of describing it. This is naturally the epistemic because I can I can tell you the temperature and pressure because I don't know what the actual positions and momenta of all the atoms are. But suppose there's a strict relation. That's just coarse graining, so there's nothing kind of fancy like universality or something going on there. That was kind of the picture I had. But in the sort of strong emergence, and maybe the other, if I'm, way out of line with how philosophers, do use it, say, but I'm kind of acquainting ontological emergence. I think that was what was in the back of the original question, where that's not the case, right? I can keep the same. It would be as if, the molecules in the gas could all be at the same position and momentum, but the temperature is different. Because it just doesn't reduce to the lower. It's ontological in the sense that it's really a new thing. You have to think of it not just as somehow constituted from the smaller fine-grained stuff. It's its own thing because it has this kind of physical freedom. I mean, it's hard to give an example of that because in physics you tend not to think anything is like that, right? Yeah. So it's sort of right. We believe in you believe in reduction.
I think I was thinking it the other way around. I was thinking, if there's such a large class of models which actually give you anyway the same kind of emergent physics, you might as well postulate that that kind of emergent physics has its own ontology and just work with that. Whatever happens at the micro level doesn't matter.
Yeah, there's certainly.
That makes sense.
Sorry, there are philosophers who want to argue that there's a kind of question that you can pose in that situation where you do appeal to the stuff that is common to the universality class. So Bob Batterman is somebody who's made these arguments, but there's an ongoing debate in philosophy of physics whether that's really a case of emergence. And I mean, I think it's almost certainly not a strong sense of emergence like Nick was describing. And then there's a question of exactly how to classify it. But Yishen wanted to jump in on this point, I believe.
Sorry, it's not a finger. I think it's a new topic. I appreciate Nick's answer, so I can wait after Dominic's question.
Okay. Oh, Nick wants to.
Yeah, I mean, I was just going to say the classic example. I mean, I don't know why I didn't put it on the table. I mean, the classic example of what I was thinking about is strong emergence is a certain position in the view of the relation from the mind to the brain that the brain state doesn't determine the mental state.
So then the other institute that shares this building, the Brain and Mind Institute, is not redundant. If you accept strong emergence. Sorry, go ahead, Adam, if it's on this line, and then we have a different question.
Yeah, it is. I think one term, I'm just throwing more jargon out, but it's kind of related to the point that you were making. People often talk about this in terms of multiple realizability, that some higher level phenomenon could be realized by a bunch of different lower level things. So sometimes that's universality classes. Sometimes that's thinking about, if we think that the brain is, mostly computing things, we might think that mental states are multiply realizable. It could be within brain matter, within computers, but that kind of more relate. Again, it's not as strong of a form of emergence as Nick was talking about, but it is something that we do talk about, and it is taken as a sort of marker that you have something really independent going on if it can be realized in multiple ways.
Nick is jumping back in.
I'm just now worried to go back about our book. So just having said this, we're not claiming strong emergence. What Chris said is exactly that's what we're not claiming. It really is the kind of intertheoretic emergence that we have in mind. You did say that, but given I've been going on about strong emergence so much, I just wanted to stop anyone from worrying too much.
Okay, the book will be available soon. Make sure to get it on Amazon. Dominic, and then Yishan. Go ahead, Dominic.
I'm gonna change the topic to something which may be brief and somewhat self-indulgent, because it's just something I've thought about recently, and I've got lots of smart people to ask about it. The explanandum in quantum gravity often seem quite general to me, like the recovery of general relativity in some limit is like a high ambition. And there seem to be instances where there's phenomena in semi-classical physics, which would be the classic thing which may just seem to cry out for explanation. And these are specific things we should try to explain. And the one I have in mind, I just want to know what smarter people than me think about it, is black holes undergo phase transitions. So if you start spinning a black hole increasingly fast, it has a negative heat capacity, which gets increasingly negative until a particular point, a particular angular momentum in which the heat capacity becomes positive. And to the best of my knowledge, there's no good explanation of what happens at that point, what changes. The black hole just gets a little bit faster angular momentum, and this is apparent change in the class of the object from a negative heat capacity object to a positive heat capacity object, which seems like a classic thing which we should have an explanation of, an account of, which we don't. And when we're trying to do quantum gravity, that's the sort of thing which I would be convinced by. If a string theorist could come along and say, I can tell you what changes in a black hole from this to this at this angular momentum, that seems incredibly compelling to me. I just want to know if people know more about these phase transitions in black holes, and more generally about more specific explanandum for quantum gravity.
To clarify, but so is it when in the limit that you have the infinite, or you achieve it before?
No, there's a angular momentum before some intermediate point before the critical angular momentum. So it's not a critical black hole. At which point, up to that point, the specific heat capacity becomes infinitely negative. Then up beyond that point, it's infinitely positive, and then tends to zero for a critical black hole.
So, sorry, to clarify, that's before the black hole becomes extremal?
Yeah, sorry, extremal, not critical. Okay. Critical should be the word for the place where the phase transition happens. Apologies.
Just, sorry, another question, but so the framework in which you make this computation is still classical, right?
Yeah, it's GR. Yeah, Kern-Newman.
So my feeling is that this is something we should be able to solve also with general relativity. Not really.
I think Francesca's assigning students to work on this as we speak.
I guess the reason my instinct is it should be quantum gravity is because if I've got a account of a phase transition from water freezing, then there's a macroscopic thing which happens, but I can also tell a microscopic story about what happens, i.e., there's a different structure. I mean, you learn about it in GCSE physics. Like, the molecules are bumping around and now they're in a crystalline structure. And I'm great, and I understand the difference between these two states in a deeper way. And we've just got no story like that for these phase transitions. Seems more specific than a semi-classical limit. Let's get that out.
My impression is it's an excellent question, and I don't think anybody has a quick answer. So I think Fabio, go ahead.
I just want to comment. I cannot address the specific context you were asking about for spinning black holes, but for instance, if you so there are like effective models of static black holes, like Schwarzschild black hole in, for instance, let's say blue quantum gravity, although it's not really derived from blue quantum gravity, but inspired by it. It's called a polymerized black hole, where you try to include quantum correction in having correction to the space-time metric. So there, for instance, if you study thermodynamics of those black holes, actually what happens is that there is a value of the mass where essentially, so let's say if you study thermodynamics of classical Schwarzschild black hole, you have that going from large mass to small masses, the entropy is just increasing, while the specific heat is just negative. But if you now add the quantum corrections, what happens is that the entropy grows up to a certain point and then goes down up to actually to a zero value, which is the extremal configuration in which, if you want, the size of the black hole is Planckian. And the specific heat, actually, there is really a transition from negative specific heat to positive specific heat. And there was some discussion about whether actually this gives the interpretation of like a phase transition from the classical black hole to a quantum black hole, which is in some sense possibly a thermodynamically stable remnant. Just a comment on this. Although it's not dynamical process, so I cannot, let's say, trust fully this discussion, but I guess this aligns also on what people here at Western are working on in instead studying remnants from a dynamical point of view.
How are the quantum corrections? Is that just Hawking radiation, or is that coming from your quantum theory of gravity?
No. Let's say it's a way to include. So it's a phase space modification, if you want, which is inspired by the idea that, for instance, in loop quantum gravity, we don't use the gravitational connections, but holonomies of the connection. And that's induced, if you solve the equations of motions and derive the spacetime metric, this has corrections which are relevant in the hypercurvature regime. That's actually what, at least for Schwarzschild, solves the classical singularity into a transition from black to white. And if you want this microscopic stable remnant is where the sides of the horizon, so actually both black and white polar horizons, are kind of like collapsed into the transition surface, which is the space-like surface, which is resolved in the singularity.
So quantum gravity solve your questions, basically.
Well, we have to spin it to solve it.
Thank you.
Good. So there was a more general question that Dominic asked as well, which is this was one example where understanding the microscopic degrees of freedom of the black hole might contribute to understanding black hole thermodynamics. But are there other targets in phenomena that quantum gravity should explain that people want to mention? If not, you can wait until dinner time. And yeah, go ahead, Niels.
Yeah, just one more quick comment on the heat capacity question. So in the context of Newtonian mechanics, you can, for instance, model the gravithermal catastrophe and thereby understand why the heat capacity is negative in such a case. And so maybe qualitatively, heuristically, one can also already assume the level of GR why the heat capacity changes sign. But I don't know anything further. But what I could recommend is David Wallace's paper on gravitational entropy and his models in there.
Good. So Yishen had a question as well. So let's go to Yishen's question.
Yeah, but before that, let me put a small finger on the Dominic question. I think that's a great question, but still, I want to endorse Francesca's suggestion. I think there's about black holes. There are still a lot of things we can understand better. For example, when we talk about heat capacity, a lot of discussion based on the event horizon, but there are different notions of horizons and also what do we mean exactly, what is temperature and how do we define that? And there are a lot of questions we need to figure out. Apart from exact solutions, there were more powerful methodologies we can understand about black holes within GR.
And I think Francesca wants to respond to that.
Yeah. No, I just wanted to support what Yishen is saying. It is the fact that indeed, when we wanted to understand the thermodynamics of black holes, including heat capacity, directions in which we are going also with my group is to understand better covariant thermodynamics. And the link there is using quantum information, using quantities, expressing energy, expressing entropy in terms of information-based concepts. And I don't know if maybe this can help also for the question you had.
I mean, I don't know about the information. I haven't thought about that, but I definitely agree with the idea that like getting a better handle on local horizons and quasi-local horizons, like apparent horizons, is really important. I mean, I'll talk about this will come up a bit in my talk tomorrow, but I think like we're confused about how the global is encoding the local in general relativity, and like getting straight on that seems like a very sensible move for the community.
So go ahead to your more general question, or your other question.
So about my general question, I think it's actually very inspired by Dominic's question. The way, I mean, because today's thing is quantum gravity, and I think one like rationale for me to think quantum gravity is like bring us closer to truth or whatever, like powerful it is that it's not because of the aesthetic values about unification or whatever, but it's that it's an attempt to solve tension that we found in the previous theory or theory change. So, for example, Dominic's question is about like there is a tension in which we have a clash between our understanding of a classical thermodynamics and black hole thermodynamics. And also we talk about emergence. It's also a very legitimate question when we have a timeless picture and the classical understanding of space-time. And also like the Hawking radiation, maybe tomorrow we will discuss a lot, like is that really idealization, or is a like limit of something or approximation or whatever? So the interplay of different theories, the semi-classical like involved quantum gravity, quantum mechanics, and classical space-time theory. So it's really so. I think the interesting thing about quantum gravity is that it brings to us a lot of interplays between different fundamental theories, statistical mechanics, quantum mechanics, and also classical gravity. So I just want to open a discussion about like it's a general question. What do you think? Like we have a great physicist and great philosopher of physics here. What do you think that might be the interesting problem at present that both the communities of physicists and philosophers would be interested about? So what's the tension that is very like physically urgent or philosophically urgent that people want to know more about? So
Covariant thermodynamics.
I agree.
Let me mention one thing, and then I'll go to Mike. And this is, I think it's an argument I owed to Nick, actually, from a conference a while ago, which is that, and this is Nick and Craig Callender have a paper about why should we try to quantize gravity. And there are some arguments that were attempts to show that we had to quantize gravity. And I think the argument that they give, if I'm remembering it correctly, which is the most compelling, is just, I call it the overlapping domains argument. There's some phenomena that require both quantum mechanics and general relativity to describe effectively. It turns out they're not very experimentally accessible, which is a handicap for us. But there soon may be. Yeah, now the situation has changed from the article that they wrote 20 years ago. But that's just, I think, a completely compelling reason why we have to combine them. It doesn't tell us much about what to do. So yeah, sorry. So I think Mike had a hand on this, and then Wayne. Yeah, go ahead.
I really want to know what happens at Cauchy horizons. Yeah, so like, is there a deep quantum gravity reason why we could just like stop right when we get there, or do we need to worry about strange global topological features of the classical theory still like being physically relevant in a quantum gravity world?
Sorry, what's the second, like global topology about what?
So if there's some deep-seated reason why we can safely stop whenever we hit a Cauchy horizon, or if it's possible that we can keep pushing through into some sort of a region past a Cauchy horizon, or is a horizon best modeled as a new kind of physical thing with some different internal structure to it and so on?
Yeah, I think so. I mean, at least there were some other notions of like besides Cauchy horizons, for example, dynamical horizon, or even like the other kinds of quasi-local horizons that maybe Francesca will know more. But the thing is, actually, in my opinion, and there are some technical words showing that apart from the like quasi-local or global properties of the horizons, you can actually know from a very detailed study of Einstein field equations to know like the exact evolution of the horizons or whatever the trap surfaces or even dynamical horizons from the specific kinds of initial conditions, so that you know in what exact mechanism that those horizons will form, and then you can better understand like about like things inside or whatever. I don't know if that's just.
Okay, I think Wayne and Dominic, and I'm going to ask you to be brief just because we're reaching the end of our.
Okay, my question will be brief. I'm not sure the response will be. I'd like to take advantage of having this group of people in the room to ask a very naive outsider's question. And this is something that came up to my mind during the exchange between Dominic and Lee at the end of the discussion of Lee's talk. So Dominic asked or said, if we're going to have an adequate black hole thermodynamics, we should be able to put a black hole into thermal equilibrium with a heat bath to which we ascribe temperature. And Lee said, well, no, we should never talk about equilibrium for black holes. Why should I not take Dominic's conditional and Lee's response and do a modus tollens and say, well, no, we're not going to do black hole thermodynamics? Because I don't take it as a necessity that thermodynamics applies to everything, but I do know that some people do. So I just like to hear what people's responses to that. Because prima facie, having an equilibrium state and being able to be put into thermal equilibrium with something that I can ascribe a temperature to would look like necessary conditions for applying thermodynamics to something.
That's an excellent question. Dominic, and then Lee. So Dominic will go first, and then Lee will come to you in just a moment, okay?
Well, I'm sure whatever I say is going to be far more naive than what Professor Smolin says. I'll give it a go. It seems to me to be really common practice in physics for us to use possibilia which are never realized in the world. I mean, we use state spaces. We don't think all those states are realized, but we talk about them and we make inference based upon them. And so I think just because it's very plausible that there's no black hole in our universe in thermal equilibrium because the conditions required for it are very, very sensitive. To me, it's a possibility claim. Like, does it make sense, a physical sense, to talk about a black hole in thermal equilibrium? And the answer is yes, because we have these ADS models. And just because we don't think an ADS model is realized precisely in our universe doesn't mean that the conclusion of that argument is wrong. I think it's standard practice in physics to use models which aren't realized in our universe, but we think are physically plausible.
Okay, thank you. And Lee, would you like to comment on this question? Sorry. Can you hear me, Lee? Would you like to comment on the discussion of whether you can put a black hole in thermal equilibrium in a... okay. I think the answer is no. So that might be a point to end the discussion, even though it's an unusual spot. So, but let me conclude with two announcements. One is that you might have noticed that the starting times for the conference are creeping ever earlier, and unfortunately, that's true for tomorrow as well. It's the last day, so we're going to start at 9 a.m. So that's to ensure that everybody has time who's traveling in the afternoon. So we do have to show up a bit earlier. Okay. Lee, did you want to comment on the thermodynamics of black holes? We can't hear you. I'm not sure if you're speaking or.
Like so. I can see.
Yeah. We can't hear you, Lee. I'm sorry. Is it on our end? No. Okay.
I don't hear anything.
Oh, now we can hear you. Now we can hear you. Can you hear us?
Now, yes.
Good. So did you hear the question was returning to the exchange you had with Dominic about whether it's possible to put a black hole in equilibrium with a heat bath in an ADS space-time, and your comment in response to him. So Wayne was asking, perhaps black holes just are not the kind of system that we can formulate thermodynamics or apply thermodynamics to.
Well, that could be, but I know that because I partly proved the theorem a long time ago. It seems to be still true that in an ordinary space-time, that is a de Sitter or otherwise closed horizon, you cannot put a black hole in equilibrium with anything else. And so I don't think it's, and whatever the situation is in ADS, I hope I made clear that I don't find that important because we don't live in ADS. So I think it's very interesting fact about black holes that you can't put them in equilibrium. And with nearly anything, And for some time, I thought that was worth trying to see if that led to an argument that we didn't have to have quantum gravity, but didn't so far reach that.
Thank you. That was very clarifying. And we're wrapping up, Lee. Thanks again for your talk, and thanks for joining the panel discussion.
Thank you.
Yeah.